Well, thank you for joining this webinar this afternoon. This is the How SOLIDWORKS Flow Improves Valve Fittings and Piping System Efficiency. This should be, I think, part 2. So I'm an engineer just like everybody else online probably. My name's Nick Pizzateri. I'm an application engineer too for Fisher Unitech. I've been with Fisher just over 5 years now, and prior to being with Fisher Unitech, I was in the industry for 10 plus years as a mechanical design engineer, and I have my mechanical engineer's degree from University of Missouri St. Louis Joint Engineering Program with WashU. So that's a little bit of my background there. So during today's webcast here, we're going to cover some things here, and right off the bat, I like to give kind of a definition of what is SOLIDWORKS Flow Simulation, other SimFlow modules that you can get with SOLIDWORKS SimFlow, and then actually do a demo of SimFlow using the Venturi Injector here. As you can see in the screen here, that is the Venturi Injector that I'm actually going to be showing, and then a small Q&A session at the end. You can submit your questions at any time using the Q&A panel, and I will address them at the end of the presentation. So SOLIDWORKS has a pretty big portfolio of simulation products, right? And the one particular area we're going to focus on is, of course, SimFlow. So with that is there are two other actual modules that can be purchased on top of purchasing SimFlow. One being like the HVAC module, which is dedicated to heating and cooling and ventilation tools for simulating, of course, HVAC systems, right? So for any of your HVAC needs, if you're actually looking for that, that would be the HVAC module. And of course, the last one here that you can add on top of SimFlow is the electronic cooling module. So that's a dedicated thermal management study tool for accurate thermal analysis of like PCB and enclosure designs. So what is SOLIDWORKS Flow Simulation? Well, it is SOLIDWORKS Flow Simulation is an intuitive CFD or Computational Fluid Dynamics solution that is embedded within SOLIDWORKS 3D CAD that enables you to quickly and easily manipulate, or should I say simulate liquid and gas flows through and around your designs to calculate product performance and capabilities. So let's talk a bit about the Venturi Injector theory here. So when water flows into a narrow cross section, so let's say we're going into the inlet here, and it starts to go down to a narrow cross section, its velocity increases and its pressure decreases. When the pressure gets lower than the ambient atmospheric pressure, the liquid or the air is pushed through the injection tube. This would be, of course, the injection tube, and into the main line. So as you can see here on the right side of the screen here toward the bottom, of course, this is what the real-world application of what this Venturi Injector would be used for. So for people that are doing maybe farming and they want to use any kind of fertilizer, and they're pumping, let's say, water from one end to and out this end, using a Venturi Injector valve, you can suck up into this filter here, let's say a chemical into this line if you're running water through, and of course it would mix with it. So let's see a demonstration of how this would be done within SOLIDWORKS SimFlow. So with SOLIDWORKS open, this is the existing part that I have done already ahead of time. Not really anything magical about it, guys. It's basically two cylinders, one perpendicular to the other one. I went ahead and made it transparent just to be easier on the eyes to understand what's going on internally. And as you can see, I want to also show you for the Revolve Cut that I did on the inside. When it comes to Venturi Injectors, what is a critical thing is in the design aspect of it is on the main line, outlet line, I should say, is having this 5-degree, kind of cone here. So if you're going to do this on your own, guys, you might want to make sure you have this 5-degree cone going out from the inlet side. Of course, out it'd be post the injector and everything else here. Also, when it comes to SimFlow, you want to make sure that you cap off any openings that you would have on your model. So in this case, ahead of time, what I have done here is I've actually just extruded a cap or an extrusion end off of the inlet side. I also did the same for the injector inlet side, and I did the same for the outlet side. You want to make sure that these are capped off good. Basically, you want to confirm it's water sealed tight. So just like any other add-in tool within SOLIDWORKS, to turn on SimFlow, you go to, I go up here to System Options, hit the little chevron arrow drop-down listing, choose Add-ins, and of course scroll down to where you find SimFlow and turn on the SimFlow add-in. So as it's turning this on, of course, it turns on its own ribbon tool, right? I'll wait till this turns on here. And we're going to turn off the analysis preparation ribbon tool here. So this is the SimFlow ribbon tool here. Just like any other tool, it has the tendency, if you start from left and work your way right. You'll also notice that it'll put into the what could be the manager tree here. It puts in here the flow simulation analysis tree, study tree, I guess you could say. And down below here are existing projects that I have already done. But I also want to tell you that I'm going to turn on a specific, let's say, it's not really specific, but what I'm going to use for this analysis is this tester configuration. So when it comes to doing any kind of FEA or even CFD, you probably want to break it away from your production design point of view and give it its own configuration. In this case, I've given it a configuration of the name tester. So, how do we go about starting off to make an actual CFD run with SimFlow inside SOLIDWORKS? Well, what's nice within it is this nice little wizard tool that I recommend using all the time when you to create what's called these analysis projects, SimFlow projects. And I'm going to name this project, let's say, tester. And as you can see here, it's using the current configuration, so on and so forth. If I click next, it goes on and says, hey, what units would you like to use? So in this case, I'm going to use inch, pound, seconds. Maybe somebody else out there would like, maybe they use SI. You can switch to SI units to be used overall within the analysis. But in the case of this today, we're going to use inch, pound, seconds. And down below here, it actually lists, everything, the unit and the decimal value being used. If you wanted to change that, you can go in here and change that also. So since this analysis being done is not going to be done externally, we're going to do it internally. But you can choose which analysis type right off the bat right here. So we're going to do internal, and I'm also going to take into consideration a physical feature like gravity. And it's always seems to be with respect, at this point right now, we're going to do it with respect to the triad. So if I click on gravity, as you can see, it's X, Y, Z component to that, and of course it's giving gravity in inches per second squared here. Well, I'm going to put gravity not in the Z-axis. I'm going to put it in the the Y-axis. So I'm going to do copy, put 0 to that, and then paste it into the Y-axis. Click next. The next thing we're going to do is what fluid is to be used in the analysis. So there's gases that can be used. They give a whole listing of gases that can be used in the actual analysis. Liquids. In this case, I'm going to use water. So if I double click on it, it lists it down below here, project fluid to be used. And the flow type, I'm going to leave it as laminar and turbulent. But you also see there's non-Newtonian fluids that can be used for analysis. There's even applesauce and even blood in here. So that would be stuff for like non-Newtonian, compressible liquids, real gases, and even steam here. Click Next. I'm going to leave the default values for the wall conditions, adiabatic, so on and so forth. And for the initial conditions here, for thermodynamic properties and velocity parameters, I'm just going to leave the default values here. I'm not going to make any changes to that. So what happens is the project's made, and as you can see, it's listed under the project folder. And it should, if I scroll down, and here is the tester one here, which is what I just made. So right off the bat, what gets created is what's called a computational domain, which is this rectangle, three-dimensional rectangle, I should say, in the model space here. You'll also see it's listed right here in the input data folder. So what a computational domain is it's a volume fixed with respect to the coordinate system within a fluid flow field. It does remain fixed in space and can be automatically envelopes the model walls, which it did here. If you did want to change the actual size of it, you basically click on computational domain icon here, and then you can drag this bigger by clicking on the arrows to maybe go inside more or outside of the part here. In this case, I'll just stretch it out just to prove that, you can actually move it. I'm going to go ahead and hide this now, so it's not seen in the model space here. And the next thing I'm going to do is go down to, in the listing there of the SimFlow study tree there, is boundary conditions. But before we get there, let's talk a little bit more about what needs to be done and known ahead of time for a Venturi injector. So we need to determine the correct suction pressure flow rate through the Venturi, and we're going to do that in a sequence of steps here. So I'm actually going to make a clone version of the tester project because you're going to see here shortly why I'm doing that in a minute here, or I should say a few minutes here. So let's set up some boundary conditions for our two inlets and our outlet here. So boundary conditions they're required to describe where the fluid enters and exits the computational domain. It can be set for like pressure, mass flow, or even volume flow, or even velocity. So how do we do that here? So I'm going to right-click on boundary conditions and click Insert. And I'm going to focus on the inlet side, the main inlet side here. And as you can see here, there's the three types you can choose from. I'm going to choose pressure opening. And I would like to do an environment pressure of the main, or I should say the initial inlet side. And I want to choose the inside face of that opening. So I'm not going to use the outside. I'm going to choose the inside face. So right-click, select Other, and choose this face to be chosen in the selection area here. Choose Environment Pressure. And I'm going to set an environment pressure going in at 60, which would be 60 pound force per square inch here. So that's going in. Hit the green check mark. And as you can see, it gives you the little arrows here. And also, I'm going to set up two other boundary conditions, one for the injector inlet side and the other one for the main outlet side. So let's go Insert Boundary again. And for the main outlet side here, again, choosing the inside face. So select Other by right-clicking on it, choosing Select Other, choosing the inside face here. I'm going to set it to use pressure opening. And this time around, I'm going to use static pressure. And I'm going to leave it under the basically using ambient pressure here. I'm not going to change it, just use the ambient. And then I'm going to do it again for the bottom on the injector tube side here. Right-click, Insert Boundary Condition, change the pressure, and choose static pressure again for that one, and choose that inside face. Right-click, the face chosen. And for now, for the time being, I'm going to leave it as ambient pressure here. So, like I said a few minutes ago, we need to determine the correct suction pressure flow through the Venturi. So for right now, I'm actually going to suppress this one from being used because you'll see later why that is. So let's keep going down in the actual study tree here. And the next thing I'm going to set up is goals. And if I right click here, you'll see that there's global, point, surface, volume, and equation goals. But what goals are is SimFlow contains a built-in criteria to stop the solution process. So we can specify goals as physical parameters at areas of interest so that the convergence is obtained. So that's a key thing within SimFlow is it's got to be converged. So we're assuming steady state here, guys, and it's important to set goals up with steady state so the analysis actually does converge. All right. So when it comes to like global goals, those are set throughout the entire, I guess you could say, computational domain. So that's what I'm going to actually set up next here. So for a global goal, I'm going to choose, as you can see here, there's a whole listing of things that you can choose from for goals. For purposes of today, I'm just going to go with static pressure, and I can drag this out bigger here, but you know, there's minimum, max, average, maximum, bulk. I'm going to use the average static pressure for global glow. Green check mark. So there's our global goal. I'm also going to add an additional one, and I would like to concentrate on as a surface goal. So, you know, surface goal would be more of a goal set at a selected area of the actual part itself. So in this case, I'm going to set it to the surface right here, the inside surface. Select other. So I have that inside face. And I'd like to set up the, you know, even the static pressure here, right? Just like I did before on the, you know, for the global goal I set up. I want to use static pressure. So static pressure, and we'll go with average. So we've set up our goals, and we basically just keep drilling down into the actual study tree here. And as you can see right off the bat, SimFlow puts in like a global mesh. And you know, when it comes to meshing, so global meshes controls the global refinement of the basic mesh. So what is the basic mesh? Well, the basic mesh is formed by dividing the computational domain into cubes. So let's set up our global mesh here. Edit, I'm going to right click on it, choose edit definition. And as you can see here, there's an automatic type of global meshing or a manual global meshing that you could use. You know, so if I click on manual, there's a whole lot of refinement that can be done to meshing using a manual. But for purposes of this, SOLIDWORKS does a really good job with automatic meshing. And as you can see here, for the level you can set to, it's basically increasing the amount of cubes or mesh cubes being used within the computational domain. So I've set it to 3. Level 3, you could do, you know, click on things and it sets to level 3 here. But I'd like to also, since I know kind of ahead of time here, I want to refine the mesh right in this region here. And if you ever use the SOLIDWORKS simulation tool, you know that inside of, like, let's say linear stag analysis, you can do a local mesh, right, which refines the mesh in a specific region. Well, in SimFlow, you can do the same. So if I right click on mesh right now, I can choose to insert a local mesh. So this comes on, the property manager of it. And up here at the top under selection, I'm going to choose region. And I'm also going to say with respect to cylinder, because that's basically the shape of this right now that I'm wanting to refine, the area, I should say. And then this cylinder pops up here, and if I click on the green arrow and drag this up, what's nice is SOLIDWORKS actually snaps into place dead center of where this cylindrical region is internally, the cutout inside there. And then, so again, this is me dragging this manually to say I want to refine this region of the model of the mesh being used. So let's drag this in, and let me zoom in a bit here so you guys can see it online. So again, I'm saying that this region here in the green, or the aqua green, whatever you want to call it, is I want to refine the mesh even more. So under refining cells here, I'm going to set this to level 3. So it's going to be even more fine mesh within that spot. Hit the green check mark. And so now that we've set up our input data folder, let's run the analysis now. So how do we run it? Well, you could go up here in the tree, or I should say the flow simulation ribbon tool, and click run. Of course, it's going to mesh and solve. So we click run. For this particular injector, it doesn't take very long to do. I can actually, while it's actually running this and finding the convergence point of the calculation, I'm going to click on, I could say click insert, and I can click preview. And with respect to the front plane, I could view, let's say, like the pressure being done here. So this is kind of seeing a preview ahead of time while it's crunching the numbers and kind of thing. It's kind of nice. I like that. So basically, it has meshed. It says the total cells, fluid cells, and fluid cells contacting solids here. So it finishes out. And we're going to go down to now the results folder. So if I click on the drop-down listing for results, let's go ahead and collapse the input data. This is where we're going to go to next to actually see the results that came from running the analysis. So let's look at the mesh first right off the bat. So right underneath here is, if I right-click, I insert mesh. And I would like to view the mesh with respect to the XYZ plane. Of course, there's these other ones you can do it with, but let's go with XYZ. And since this is the plane on the XY that's going down the center, this gives me the ability to view the actual mesh that was done. And as you can see, that local mesh refinement that I did here, you can see how it's more refined than the rest of the actual computational domain of the part. Also, let's go down to, let's create what's called cut plots. But before I do that, let's right-click and hide the mesh so I'm not seeing that here. So let's create some cut plots. So what are cut plots? So cut plots display results on any SOLIDWORKS plane. So we want to observe the results on a plane, let's say. So for the front plane here, I'm going to go with choosing to see the contours, which is of course the coloring, of course, within that, and the vector arrows within that. Under contours, I'm going to change this to view the velocity. So we would like to see that, you know, as the fluid flows through here, that once it hits this cone area, that it increases velocity. So I've set that to velocity. We're good to go. Hit the green check mark. And as you can see, with the vector arrow showing the actual, you know, fluid flow through the valve here, as you can see in the actual color scheme here, 0 is of course blue all the way to red, and of course it gives the units in inches per second, right? So that's velocity. And as we're going down the main inlet here, we get to this, our velocity does increase. But it's interesting how it increases and it just kind of sprays up in the spot here. And as you go down, it kind of circles back around here. So that's velocity. So let's rename this in the tree by slowly double-clicking on it and typing in velocity. Let's also set up another cut plot of, I actually meant to hide, let me hide the velocity one here. And let's do a velocity, or I'm sorry, let's do a cut plot on the front plane again of, let's say, the static pressure. So let's go under velocity, let's choose pressure, which of course in this case would be the static pressure, and hit the green check mark. And right now we're not getting really good results, but I'm going to change this to 0. And as you can see, our pressure is high, but it goes low. It is getting, it's very high here, but it also reduces right in this spot to 0, which is theoretically what it would be doing, right? So, like I said earlier, the velocity increases, but the pressure decreases. So because of that pressure decreasing, we're getting this upward suction in this injector area going into this. It's almost like a vacuum effect, or I guess you could say in some ways like a buoyancy. Like an air bubble in water, buoyancy pulls it up. And so we'll call this static pressure. So there is our cut plot of the static pressure. So we'll go ahead and right click and hide this. And just kind of working our way down the results folder here of the study tree here. Let's also see an actual animation of the flow trajectories. So if I right click on flow trajectory and click insert, let's do one of the main inlet side here. So again, choosing the inside face, let's right click, select other, choose the inside face. And let's set this to, I don't know, we'll go with like 100. And so this is, when I say 100, this is the number of points that are going to be used off that face. And I'm going to set to use, of course, static trajectories, and I'm going to use arrows. Or I'm going to say lines and arrows, put it that way. And I'm going to set this value to 0.00393 or something like that. And make sure this is the color pressure is on. Hit the green check mark. And this is kind of the end result of the animation. But if I right click on it and choose play, it actually plays the animation of what would be going on there. But as you can see, like I said on the one cut plot, there is this turning back that occurs within the valve. So let's, down below here is a stop all button that stops the animation. And if I right click, let's hide this. Now let's see what flow trajectory is right now in the injector inlet side. Probably not a whole lot going on there. So let's see here. So let's choose not that face, but the face down below here. So let's right click, select other. Didn't choose it. Let's do it again here. Zoom out a little bit. Try it again here. Let's go back out and go back in. Select other. There we go. So we selected that small inside face. Let's go with 200 points there. And let's choose arrows. And of course, pressure being shown. Let's see what happens here. And again, like I said, it's not really doing what we want it to do. So let's even animate it here. And things are just not right there. So what we need to do, and let's stop that animation and hide this here. You're going to see here in a few minutes after setting up some other results here what needs to be done. So let's progress on here. So we can also choose to set what's called surface parameters. So surface parameters can be used to determine pressures, forces, and any other thing on any face within the model that is actually contacting the fluid. So how would I set that up? Let's right click, and let's say on this face here, let's do, let's say something like, what if I wanted to see the volume flow right there? I click on that, volume flow rate option. And if I click show, or let's hit the green check mark, and then right click and say show. Can I compute? Okay. It's not computing it because there is a problem there. And let's do another one. Let's do it at the main inlet side here. So let's right click, select other. And let's also do a volume flow rate there also. So if I click show, it probably does show it. Oh, it's actually got two phases involved here. So let's right click, clear. And let's go back out and come back in here. So let's see, that's that one. Let's delete that guy. So that one is for that one. Let's right click, insert, and do the inside face here. And we want to see the volume flow rate. And so right now the volume flow rate is showing to be 79 inches cubed per second here. So let's hide this for the time being. And let's do one more thing on our input, our results drop-down listing here, and that is a goal plot. So goal plots allow you to basically see how a goal changes throughout the flow simulation, as well as the final flow of the goal at the end of the calculation. So if I was to right click here and say end result, let's say for the surface goal, which is this guy here, what was the actual average static pressure we were getting there? Because that's something we need to know. So if I click show, it's giving me an average static pressure of like 60 here. Now it does say negative 60. You know, I'm going to put in the value of 60 here shortly. So leaving that, or remembering that value of 60 here, let's hit the green check mark. Now, like I said earlier, I'm going to set up two different studies here, and I'm going to clone the tester one here. So if I right click on it and choose clone, I'm going to say tester, let's say _2, and I'm going to use the current configuration in this. And now I'm on, since this is highlighted in the actual tree here, I'm on tester 2, but this is where I'm going to right click under static pressure and unsuppress this, and then I'm going to edit this and add in the static pressure value of 60 here. So if I click 60, hit the green check mark, and I'm going to run the analysis again with that value inputted in there. So click run, it's going to mesh and solve. And just for purposes of the simulation, or the actual sim flow run here, this will take a little bit of time. I'm kind of running out of time here, guys. I'm going to get to some questions. I'm going to go ahead and stop this for the time being, because I have ran this ahead of time in another run, and this is under the webcast run. I'm going to activate that one, and then I want to actually show you guys what is the actual result from that under the flow trajectories here. So if I right click and I say, I got to load results on that one. And if I right click on this and I click play, as you can see here, we're getting a very good result of our injector inlet out here of the pressure. So red being high, and as you can see, we're getting this pressure build up here of the suction going through that. And then also let's see it from the main inlet side here. So if we click play, so from the main inlet side going in here. So this is the end result of the parameters we set up, and the end result of the trajectories that would be shown here. So we're it's pretty much proving that using the Venturi Injector design, you can suck things up from the injector tube side to, let's say, like I said earlier, if you want to put any chemical into your water line with this model, you can also simulate it within SimFlow. So so guys, that really kind of really, guys, thank you for joining us today. This concludes the presentation portion of our webcast.